All right, so welcome back. Today's topic is maximum likelihood estimators. So what's the idea of the maximum likelihood estimator? So maximum likelihood estimators. Okay, so the idea here is pretty natural. So if we so imagine we have some population with some unknown distribution. So population described by some distribution. Well, we know something about it. We know its general form, but there's some unknown parameter, let's say theta. And if we observe some particular value, x equals, let's say, some little x naught, and we want to guess this parameter theta, then what do? We just we guess a value for theta, which maximizes the probability density function. We'll call it g of theta, which is f theta of x naught. So we just find the value of theta that maximizes the value of our density function. Okay, so just to get a flavor for this, in not the kind of density case, but actually in the discrete, even finite case, let's just play the following little game. So let's do a finite example, just to get the flavor of it. So, okay, suppose we have 5 people, and they take a test. So some number pass and some number fail, and we want to estimate the number that pass. So let's call that the unknown parameter theta. And what do? We take some sample. So we pick at random, let's say 3 people. Of them, let's say 2 pass and 1 failed. And then we're going to then guess from that how many people over the total population passed and failed. So really there's this unknown parameter theta. It can a priori have values 1, 2, 3, 4, or 5. Of course, we can see just at the outset that some of these values can't happen. If we know that at least 2 people passed, then 0 and 1 are not possible. And if we know that at least one of them failed, then not all 5 people passed. And so that really leaves us with the possibility of either 2, 3, or 4 people. And so what do? We just say, well, what's the probability that we made our observation? I'll just say probability of observation. I don't feel like writing, the 2 pass, 1 failed thing, but let's just say probability of observation given some particular value for theta. And so in particular, I can say what's the probability given that theta is equal to 0, as we've seen. That's really 0. Probability if theta is 1 is also 0. What's the probability that we made our observation if we know theta is 2, though? Okay, so if we know theta is 2 and we choose 2 people at random or 3 people at random and 2 passed, 1 failed, well, that's really saying that of the 2 people that passed, we choose both of them out of the 3 people that failed, we chose one of those. And that's of all the different ways we could have chosen from the 5 people, 3 people. Okay, so altogether, that's 1 times 3 divided by 5 choose 3 is 10. So that's 30%, 3 out of 10. What's the probability that we made our observation if 3 people pass? Well, that means that out of the 3 people that passed, we chose 2 of them because we chose 2 that passed. And out of the 2 people that failed, we chose 1 of them. And that's, again, divided by 5 choose 3. So we got 3 times 2 over 10, so 6 out of 10. The probability, if it was 4, would have been, well, out of the 4 people that passed, we chose 2 of them, and out of the 1 person who didn't, we chose them, and that's out of all the ways of choosing that. And again, we got let's see, that's 6 times 1 divided by 10, that's 6 out of 10. And finally, the probability if theta was 5, as we noticed before, was 0, because at least one person failed that we picked. Okay, and so what do we find? We find that in this case, we actually don't have a unique answer. These two possibilities are both the possibilities that maximize the probability. And so we get, so in this case, notice it's not unique, but most likely are the values theta equals 3 and theta equals 4. It's not like those values are most likely, it's that the chance of making our observations were most likely given those theta values. Okay, so so just a few comments then about these estimators. So remarks about these maximum likelihood estimators. Well, so they don't need to be unique. But in a lot of natural cases with continuous variables, they often are unique. You know, often unique for common distributions in the continuous case, and with certain assumptions that I'm not sure if I'll really have a chance to cover, they are consistent. So I mean, you know, to prove consistency, you basically want to know that that these kind of parameters are kind of naturally, uniquely like solvable by doing this maximization thing, and you need a few kind of continuity assumptions and things like that. But so let me not go into that. But under reasonable assumptions, they're actually consistent. And also, they are in some sense minimal variance. So they're not unbiased estimators. That's a good thing to point out. They don't have to be unbiased. And so, but you know, there are minimal variance in some asymptotic sense in terms of in terms of their consistency. Okay. But let's see. Okay, they don't have to be unbiased, but they have the so-called invariance property. Which is a pretty reasonable trade-off if you're not going to be, if you're going to have to be biased, which is that if you have a maximum likelihood estimator for theta, then you can apply a function to it to get a maximum likelihood estimator for g of theta, if g is continuous. So, as we've seen, it's typically the case that that if you have an unbiased estimator for some parameter theta, like if this is unbiased for this, then this thing will like very often be biased as an estimator for that. But on the other hand, this maximum likelihood property is preserved, and so at least you're going to get you know, so you get some reasonable method for consistent low variance estimators, even if they are biased. Okay, so next, why don't we work an example, a more interesting example. So I'm just going to play with something from the normal distribution. Okay, so let's suppose I have a normal population, just for practice, let's suppose that I have a known variance of, I don't know, let's say 3. Mu is unknown. And so I imagine that I have a density function which depends on my unknown mean. So this is just given in the standard way. Square root of sigma squared, sigma squared is 3 times 2 pi e to the minus 1 over twice sigma squared, which is 6. I guess I could have called that other thing a 6. X minus mu is the unknown squared. Okay. And so, right, okay. So then if we observe with, let's say, n equals 12, a sample mean of 15, what is a maximum likelihood estimate for mu? In other words, what I'm asking is what value of mu, so which value of mu maximizes now I really am talking about the joint density function f mu of x1 through xn if x bar is 15. Okay, so let's just go ahead and do that. So of course our joint distribution function, because we're always talking about some IID variables representing our sample, x1 through xn, of course n is 12 in this case. And so because we're talking about some independent variables, the joint distribution function is going to be the product of my distributions, of my density functions, excuse me. And so we get that this f mu of, let me call it, of x vector is 1 over root 6 pi e to the minus 1/6. So when I multiply these all together, I get a summation of the exponent, and it's xi minus mu squared, I equals 1 to 12. Okay, that's my joint density function. Now, you might see that here I have a bunch of xi's, but I'm really trying to deal with this x bar. And so I'm going to use this trick that we've seen before. I'm not sure if I'm going to how many times I'm going to keep deriving it, but let me let's take a look at this usual trick of if I look at this thing in the exponent, which is this summation, then I can write this as in this way by adding and subtracting x bar. Okay, and then if I do that and actually square it out and distribute all that stuff, I get my squared term there, I get my squared term there, and then I get the cross terms, which are twice these xi minus x bars, x bar minus mu. Okay, now of course the x bar minus mu is just kind of going along for the ride in the summation. It doesn't depend on the index, so I can pull it out. Xi s bar squared. So this is just n of these. N is 12 actually for us. So 12 times, let me keep it as an n for now, n x bar minus mu squared. And then that last thing, I can again pull out that x bar minus mu, and I get a sum of xi minus x bar. And then what we find is that this sum is actually 0, because if I just do that off to the side, xi minus x bar, so this is the sum of the xi's minus the sum of the x bar. I mean, the sum of the xi's is n times x bar, and because that I just have n x bars, that's that's 0. Okay, so altogether, what do I get? I find that that this is a reasonable way to rewrite that, which is my exponent up here. So let me just grab that expression. And what we get for our for our joint density function then is 1 over root 6 pi e to the minus 1/6 of sum I equals 1 to 12 now of xi minus x bar. Whoops. Wait, what did xi? Yeah, xi minus x bar, and then x bar minus mu, and then so e to the minus 1/6 times n, so that's 12, and then x bar minus mu. I think that's what I have over there. Right, yeah, so it's this expression that's replacing this expression, and that's what I've done there. Okay, oh, I need to square those. Yeah, okay. Okay, good. So, yeah, so now what are we doing? We have this expression, and we are trying to choose mu to maximize this expression. And what you can see is that of these terms, there's no mu going on in any of that stuff. So changing mu doesn't do anything except for this part of the expression. And so really, I'm maximizing that third term. And that's just maximizing a normal distribution centered at mu. And, well, the maximum happens at mu, right? Which, we could use a little calculus for if we wanted to, but let's just, notice that we know the answer. So maximum at x bar equals mu. And so that means that our MLE estimator for mu is x bar. So in other words, it's the random variable x bar. So in other words, the sample mean is the maximum likelihood estimator for the mean in this particular case. Okay, that was a lot of work for a kind of anticlimactic answer. Let's, but spurred on by that wonderful success, let's just take a look at the general case of a normal distribution, but this time where both mu and sigma squared are unknown. So this maximum likelihood estimation process we can do simultaneously for various parameters by finding the value that that maximizes, based on moving both of those unknowns at the same time. So really now I'm thinking about f of mu sigma squared of x bar. This is given by the by this joint density function as follows, gotten by multiplying a bunch of standard normal distributions, a bunch of normal distributions together with the same mu and sigma squared. So I got minus 1 over 2 sigma squared, and then the sum of these xi minus mu squareds. And just like before, just to skip the algebra, you can do the same algebraic manipulation to break up this exponential in these same two factors. So let me just go ahead and do that. So the sum I equals 1 to n of, on the one hand, xi minus x bar, and then times e to the minus 1 over 2 sigma squared, times an n there too, x bar minus mu. And these are both squared. Okay, so now we want to solve for mu and sigma squared, which maximize this. And so just as before, what you can see is that whatever value I happen to choose for sigma squared, if I'm then looking for a mu that is the best possible thing, then none of these expressions involve the mu except for this last one. And that's where the maximum happens at x bar. So just like before, we'll find that the maximum always is at mu equals x bar. But the question is then, what about for sigma squared? So, I'm going to then, to figure that out, what you would want to do in principle is do, for example, the partial derivative with respect to sigma squared of this expression. And, we look at this thing and we're like, look at this expression, let's say this one over here, and we're like, take the derivative of that with respect to sigma squared. Let's see, I got the sigma squared in here. I have a sigma squared over there. That looks like I have to do like a chain rule and product rule and then some chain rule stuff. And oh, what a pain! What a pain! Like why would I do that, right? Why would I want to do that to myself, right? So let's not do that. Instead, let's just observe that maximizing f of mu sigma squared is the same as maximizing its logarithm. And if I take the logarithm of this expression, then I get rid of all those, chain rules and all that stuff. It's just, and product rules or whatever, it just gets a lot easier. So let me take this expression here. And let's move it down here. And let's take its logarithm. Actually, it might be a little bit more kind of easy to conceive if I make the substitution like v for variance as sigma squared. Then what I'm looking at is this f of mu comma v of x bar is 1 over 2 pi v n over 2 e to the minus 1 over 2v sum of xi minus mu squared. Just a little easier to look at that like a variable, right? Sigma squared is the variable that we're looking at. Okay, so now if I take the ln of that, then that's, what is that? That's in halves, minus in halves, I guess, ln of 2 pi plus ln of v, then minus 1 over 2v sum of the xi minus mu squared. Right. Okay. And let's see. So this is, yeah, okay, that's what it is. Now let me take the d by dv of that same expression. So, of course, this term is a constant. This I'll get a 1 over. This thing is a constant with respect to v, and this thing I'll get the 1 over guy. Or, sorry, I get the minus 1 over, thing squared guy. Okay, whatever. Okay, so you get minus n over 2 times 1 over v, and then minus 1 over 2v squared or plus with the little chain rule there. And then this is just a constant, xi minus mu squared. Okay. And so then I get, what do I get? Yeah, I get this expression. I want to set this thing equal to 0. I'm going to solve for that thing equal to 0. So if that thing is equal to 0, I can multiply, for example, by 2v squared and set that equal to 0. That's a little bit easier to look at. So let's see, what do I get? I get minus n times v plus the sum of xi minus mu squared is equal to 0. And so that means I want to set v equal to what? The sum of xi minus mu squared over n. But what am I doing with this square? Yeah, that's right, over n. Okay, so I want to set v equal to that, and as we said before, I want to set mu equal to x bar. And so altogether, I get that my MLE estimators are mu equals x bar, and v equals, well, that expression, sum of xi minus, well, my value for mu is going to be x bar squared over n. Does So this is sigma squared. And so what do we find? This is kind of interesting. We see, so this is not a surprise for our estimator. So just these are, I've just put values here, but what I guess I really should have said, like, let's say mu hat, for example, this random variable, x bar is my MLE estimator for mu, and sigma hat squared being this sum of xi minus x bar over n is my MLE estimator for the variance. So this is kind of neat. We see that the denominator of n comes in instead of n minus 1, which tells us, because when we had an n minus 1, that's an unbiased estimator, this actually will have a bias. But even though it's a biased estimator, it is a MLE estimator for a maximal likelihood estimator for the variance. And because because these have the invariance property, notice that also says that if I let sigma hat be the square root of this thing, xi minus x bar squared over n, then this is an MLE estimator for the standard deviation. So of course, these might be biased, but these are consistent minimal variance estimators, and so that's a nice thing to see.